All right, this is lecture 10 for Psych 1040, in which I'm going to introduce the t-test to you. Now, you've, in the last week, learned about how to test hypotheses about a sample mean, and that particular hypothesis test was called the z-test. And you can see the formula there where we computed a z by taking the sample mean and then subtracting the population mean defined by the null hypothesis, and then dividing it by the standard error of the mean. And then whatever that z-score was, we compare that to a critical value to decide whether or not to reject the null hypothesis. And as it says here, this is good to use when we're testing differences between means when the population standard deviation is known. However, what about when the population standard deviation is not known? All the problems that I've given you to this point always involved knowing the population standard deviation or the population variance. So now what we're going to do is we're going to deal with a new kind of test where we don't know the population standard deviation or variance. It's not given to us. And in that case, we're going to be using what's called the t-test. And if you just look at the formula for the t-test, it looks very similar to the one for the z-test. In the numerator, we have the mean minus the mu. And then down below, we have this thing that looks like the standard error of the mean, even has a little sub m. But this time, that s is not a sigma, it's an s. And that's going to tell us that it's going to be an estimate of the standard error of the mean. So that's going to be the primary difference between these two kinds of tests. Now, before we get into the actual mechanics of conducting a hypothesis test with the t-test, let's go ahead and talk a little bit about the background for the t-test in the first place. And what's interesting in the history of statistics is that Guinness beer is actually responsible for us having a t-test. And it's not because someone drank a lot of Guinness and sat down one night while they had 4 or 5 pints and then decided to make a t-test. Now, this fellow that you see in this picture was a guy named William Seeley Gossett, who lived from 1876 to 1937. And around the turn of the last century, Gossett had a job where he was working for the Guinness brewery in Dublin. And he was a statistician. He had been trained in England. And one of the ways that he could get some money was being a statistician for the Guinness brewery. And you might wonder, why would Guinness need to have a statistician on staff? Well, what they were concerned with was being able to figure out which samples of barley they should be buying from different farmers that are providing the ingredients to make up the beer. So if you can imagine, you're out there buying, the different wares that farmers might have in terms of their barley that they're trying to sell you, and you're trying to decide whether or not the quality of that barley is really going to be that good. But you can't look through all of the barley. So what you do is you take small samples of the barley from this farmer and from this farmer and this farmer to help you decide which one is the best yielding kind of barley for the beer. And so as part of that problem of dealing with small samples and then trying to generalize to the population of all barley from that farmer, he came up with the t-test. And it's interesting is that the t-test and this t-distribution are very powerful. It's used in psychology and used in lots of different disciplines, but it really had that primary purpose of just helping out Guinness. But the thing is, Gossett knew that this was actually something important, so he wanted to publish it in a mathematical journal and make sure that other people, statisticians, could see it. But because he was under obligation to work for Guinness, and he didn't want, the Guinness was not supposed to be funding his sideline activities and academics, he decided to publish these papers with the pseudonym Student. Not a very clever name for a pseudonym, but in fact, every time he published one of these papers about the t-test, he said the author's name was Student. And so it became known as the Student t-test or the Student t-distribution, when it was really this William Seeley Gossett who had written all these papers. Okay, so that's a little bit of a background and how Guinness is responsible for the t-test that we have today. Now, how does a t-test really differ from a z-test? Well, a t-test uses an estimate, like I said before, of the population standard deviation based on the sample standard deviation to produce an estimate of the standard error of the mean. Unlike a z-test, each t-test also has associated with it a certain number of degrees of freedom. So we're going to have this concept, degrees of freedom, that's related to the sample size and the number of parameters that are being estimated. And a third way that a t-test differs from a z-test is that a t-test is based on a t-distribution, whereas a z-test is based on a normal distribution. Let's take that first item here about how the t-test differs from a z-test. And as I said, we're going to have to estimate the standard error because we don't actually know the population standard deviation to calculate it. So in hypothesis testing, we normally want to use a comparison distribution, like the distribution of means. And when you know the population standard deviation, if you're trying to figure out what the spread of that distribution of means is for a given sample size, you would go ahead and compute the standard error, thing that we covered in the last lecture. But now the problem is we don't know the population standard deviation. So if we don't know it, we're going to have to estimate it. And the way that we estimate it is by using this formula. So basically what we're going to do is we're going to figure out what the standard error of the mean is by taking the population standard deviation and dividing it by the square root of n. Okay? So that's going to be our new way of measuring the population standard deviation. So these two things that we have here are the variance for the distribution of means and the standard deviation for the distribution of the means. So one on the left is the variance, the one on the right is the standard deviation or the standard error. And you can see that in both cases, we're going to have to use estimates of the population variance and the population standard deviation in order to figure out what the standard error is of this comparison distribution. So that means that we're not going to use the population standard deviation number given to us, obviously. We're going to have to calculate an estimate of it from our own sample. So we're going to have to actually know our sample's standard deviation. And we want the unbiased estimate version of this. So we want to use the n-1 version that we compute to get the population standard deviation or the population variance. Okay, so that's why we have an S here instead of a Greek letter sigma. Now, when we don't know this population standard deviation, the shape of our comparison distribution is also different. This is one of the things that the student figured out. Our distribution of means doesn't necessarily follow the shape of a normal curve. What Gossett determined is that when we're estimating the standard error, the distribution of the means is going to be following a t-distribution. And its exact shape depends on the degrees of freedom that are used to make this standard error estimate. In this case, the degrees of freedom is n-1, because you remember, we make this adjustment when we go ahead and estimate the population standard deviation, this unbiased estimate, and we correct our estimate to make it unbiased by using an n-1 in the denominator rather than an n. And because of that n-1, that means then our degrees of freedom is n-1. And so the t-distribution is going to have these degrees of freedom to tell us about the particular shape of any given t-distribution. So this is analogous to the way that in the distribution of the means, it does matter what the sample size is, because you can see here the sample size, there's the n, and then we're subtracting 1 in this case to get our degrees of freedom. So instead of talking about sample sizes or n's, we're going to be talking about degrees of freedom when we talk about the t-distribution. I want to go ahead and just make a slight detour here and talk a little bit more about degrees of freedom. So again, this n-1 correction has a special name, degrees of freedom. And this term refers to the number of values that are free to vary when you're estimating a parameter. Okay, so that's why we call it degrees of freedom. It's the number of values that are free to vary when you're estimating a parameter. For example, if we were to choose 4 numbers that have to add up to 100, okay, so that's what a rule was, that we have to choose 4 numbers that add to 100. And I say, okay, well, the first number is 25, the second number is 20, and the third number I pick is 25. Notice, though, that the fourth number has to now be 20 in order to make this add up to 100. So that means that the fourth number actually wasn't free to vary. Once we went ahead and determined what the last number should be 30. Once we figured out what the first 3 numbers were, that determined what the fourth number was. So in this case, only 3 of the numbers are actually free to vary. In this case, for instance, we have 50 plus 20 plus 10, and I say, I got to choose 50, I got to choose 20, I got to choose 10, but I won't be able to choose the next one here, which is 20, because that is not free to vary. It has to be 20 in order for the other numbers to add up to 100. And then a case again here, if I have 110 plus 8 plus 5, it turns out that the fourth number again, it would already be predetermined once I knew what the other 3 numbers are. So in fact, I only have 3 numbers here that I'm free to choose. So that would mean that all of these problems have only 3 degrees of freedom. the fourth number isn't free to vary. It's determined by what the other three numbers are. That's the closest I can come to trying to explain at this point what we mean by degrees of freedom. And basically that logic that I just gave you here in this little example is how we use it in statistical formulas. So statistical formulas that use degrees of freedom will always include a formula to help you compute the degrees of freedom. So you don't have to actually work through the formula to figure out how many of the values are free to vary. So instead of like having to figure this out, like, okay, if I have these four numbers, only three of them are free to vary, my degrees of freedom is 3, I would just tell you the formula here is degrees of freedom is equal to 3, or whatever it happens to be. So from now on, every time we mention degrees of freedom, we'll give you a formula for that specific problem to know what the degrees of freedom is. Now, as I said, student discovered that his t distribution that he was interested in changed based on the degrees of freedom. So the shape of it is different. And so this is, again, analogous to our distribution of means when it was a normal curve. And we knew that as the sample size increased for the distribution of means, we got different shaped distributions. So here again, we have different shaped distributions that are partly being determined by the sample size. But instead of saying the sample size here, we're using the degrees of freedom. So the bluish line there, that the darkest blue is where we have a degrees of freedom of 1. Then we have red, degrees of freedom is 5, and so on. When you get up to about degrees of freedom of 30 or higher, you're getting closer and closer to what a normal curve is, which is also superimposed there. So it's really numbers that have degrees of freedom less than 30 where we find that the curve deviates more from a normal curve. So everything less than 30 is not really following a normal curve. All right, given all of that, let's go ahead now and try to compute a hypothesis test using this t distribution, and we'll see if you can figure out why we'd be doing it this way. All right, let's start out with a single sample t-test. So what you were doing last week was a single sample z-test. So what we'll have here is one sample mean, and we'll want to know if it's different from some other score that we are hypothesizing about. So when we're hypothesis testing with the t, we're going to have to use a different table to determine our cutoff scores because of the shape of the t distribution is different from a normal curve. So we use table A-2 to determine the cutoff score for t when deciding to reject the null hypothesis. So this is at the end of this chapter 7. They have a table A2 there that you maybe want to photocopy, and I also will make one available up on Blackboard. Now, you can also use programs like SPSS that will give you the probability of t if the null hypothesis is true. So you can get the exact values of that when you normally do a t-test, for instance, in SPSS. But for now, since we're doing this by hand, you'll need to use table A2 to determine this cutoff. All right, so let's go ahead and go through a computational example with a single sample mean. You've read that the typical Year 12 student can identify 32 out of 70 countries on a map of the world. You give this test to 10 students in your Year 7 geography class. And the question is, are your students different from the average Year 12 students? Okay, so we have 10 students who've been given this test, and we want to know if our 10 students maybe come from a population that's different from what the Year 12 students is like. Now you'll notice in this problem that we don't know the population standard deviation or the population variance. All we know is that the population mean is 32, that the typical Year 12 student gets a score of 32, and that means the average, okay? And we're going to have to then therefore use a t-test to do our hypothesis test rather than the z-test that we used last time. The other thing we're missing right now is the data. So here's a screen that shows you the data. So what you can see in the first column are my 10 students, and then the next column over is their scores, what they got on that geography test. And what I'm doing there is I'm going ahead and continuing on to figure out their standard deviation or their variance. And what you'll see that I've done is I've gone ahead and created totals for each column. So like for instance on the X, they total up to 425. And so if I divide by 10, that tells me my sample mean, which is 42.5. Then what I did is I took 42.5 and we subtracted it from 32. So it's X minus the mean. And that gives us minus 10.5, 16.5, 18.5, and so on. So the rest of those numbers there are all X minus this mean of 42.5. And then finally, the last column is taking each of those differences between the x and the mean, these deviations, and squaring them. And so now I have squared deviations in the final column, 110.25, 272.25, and so on. And if I sum all of those, I'll have the sum of the squared deviations. Then what I need to do, of course, is divide that by n minus 1, and I'll have the population variance, the sample variance, and if I go ahead and take the square root, I'll have the sample standard deviation. Okay, we'll come back to these numbers in a moment. Let's go through now our 5 steps of hypothesis testing using the t-test. So step 1 is restate the question as a research hypothesis and a null hypothesis about these populations. And the null hypothesis here is going to be that this group of 10 students that I have in this geography class come from the same population as the year 12 students who take the test, and they have a mean of 32. If I can reject the null hypothesis, then I'll say that my students come from a different population that has a mean that's not equal to 32. Okay? Now, in step 2, I want to go ahead and determine the characteristics of my comparison distribution. So if I go across the top here, first of all, I need to know what's the population mean, and I get that from the null hypothesis. And the null hypothesis says that mu is equal to 32. Another characteristic that I want to know about my comparison distribution is what its variance is. Now, I wasn't given it, so I have to estimate it from the sample. And I can estimate it using what we learned many weeks ago, s squared. So that's my estimate of the population variance, my unbiased estimate, where I go ahead and take the sum of those deviation scores squared and divide by n minus 1. So I have my SS over n minus 1. And what you can see in the next column over is the calculation for that. And that turned out to be 1,268.5. That's the SS. And then I'm dividing it by 9 because it's 10 minus 1. So I get 9. And then that reduces down to 140.94. So that's my estimate of the population variance from my sample. And then I need to calculate the standard error from that. And the formula for the standard error is what you see here. So I'm going to compute the standard error based on this estimate of the population variance or the population standard deviation. And so you can see here, I get this little s sub m, and that s sub m again is the standard error. That's our estimate of the standard error for this comparison distribution. And what it says is I need to go ahead and take the variance and divide it by the n, not the n minus 1, the n, and then take the square root of it, or I can take my s, which is my standard deviation, and divide by the square root of n. Either way it works. And so over on the next right column, you can see that I went ahead and took the square root of my variance and got the s. That's 11.87. And then the next step was to take that 11.87 and divide it by the square root of n. Again, the square root of n here is, the number is 10 is for my n. It's not n minus 1. So we only use the n minus 1 when we're making an estimate of the population variance. Now with the standard error, I'm basing my standard error on that estimate, so I don't take another n minus 1. So anyway, I got my SM here, 11.87 over 3.16, and that comes out to be 3.75. So 3.75 is the estimate of the standard error. What about the shape of the distribution? That's the other thing, another characteristic that we're interested in. And remember that this is now a t-distribution rather than a normal curve distribution like we used in the z-test. So it's a t-distribution, and the t-distribution changes based on what the degrees of freedom is, and the degrees of freedom here is n minus 1. So I'll need to look it up in the table for degrees of freedom of 9 when I want to get an idea of exactly where the cutoffs are and that kind of thing for this particular shape of this distribution. So again, all of those numbers that I used to figure out what my population estimate of the population variance was, this unbiased estimate, is by taking that last column, which becomes my sum of squares down there in the lower right corner, 1,268.5, dividing it by n minus 1 because I want an unbiased estimate of the population variance. And then that gave me my population variance, took the square root of that to get my estimate of the population standard deviation, my unbiased estimate of it. And then I took that and turned that into the standard error. Hypothesis testing step 3. Now the next thing I want to do is I want to determine the significance cutoff using the t-table. So I want to go ahead and find my critical values where I'm going to go ahead and cut things off. So here's table A2, and you can see it's very similar in the way it's kind of set up to what the normal curve looked like. Except this time, you can see that we have degrees of freedom in the first column rather than anything else like z-scores. And so what you're going to do is once you figure out your degrees of freedom is go down to the line that has your degrees of freedom. And then you can see that it's divided into having 3 columns for one-tailed test and 3 columns for two-tailed tests at alpha 0.1, alpha 0.05, or alpha 0.01. So let's go ahead and look at ours. This would be here. So our degrees of freedom is 9 because it's 10 minus 1. We're doing a two-tailed test because it didn't say anything else, and we want an alpha 0.05. So you can see then that our cutoff is going to be 2.262. That's 2.262 above and 2.262 below. So our t-distribution has that as its cutoff values. That's going to mark off the top 2.5% of the t's and the bottom 2.5% of the t's. Or another way to look at this, here's the d-distribution where the degrees of freedom is equal to 9. I've marked off that plus 2.262 and minus 2.262 are the places where we have the bottom and top 2.5%. So that means that our cutoff is plus or minus 2.262. Now, step 4. We want to determine our sample score on that comparison distribution. We need to know, where does our sample, when you convert it to a t, line up on that comparison distribution. Our sample's mean was 42.5, so it's higher than what year 12 students do, but is that high enough? Is it going to be something that exceeds the cutoff once we convert it to a t? So what we want to do again is look back to our numbers here, and we can figure out that our 42.5 is basically those x's divided by 10. That gives us 42.5. And we want to plug in that 42.5 as our sample mean. The mu is 32, because that's what the null hypothesis says, that come from a population where mu is equal to 32. And then the thing that's in the denominator is our estimate of the standard error, which was 3.75. So that reduces down to 1.44 over 3.75, and that gives us a t-value then of 2.8. So our t is 2.8. That means then we're ready for step 5, where we're going to decide whether or not we want to reject the null hypothesis. Our obtained t was 2.80. So that exceeds the cutoff of plus or minus 2.262. And that would mean then we would reject the HO. That our sample of year 10 students who are doing exceptionally well in this geography test are actually coming from a population that does not have a mean of 32. So they're not like those year 12 students after all. So again, here's where our t is in blue, that 2.80, far exceeding the cutoff and allowing us to reject the null hypothesis. How you would report this is you could say in your little report, the year 7 students differed from the year 12 students, t 9, and that's in brackets is the degrees of freedom, as you can see there. So the t is italicized, 9's in brackets. Then we have an equal sign, and there's our obtained t. So we actually, our obtained t was, 2.80. And so we put that there, and then our p-value is less than 0.05. So I just want to remind you that that example, even though we ended up comparing two means, we only had one sample, just our year 7 students. And we had some general knowledge about year 12 students, how they do maybe like nationally on that geography test. And we were taking our sample and comparing it to that population mean. That's all we were doing in that t-test for a single sample mean. Now look at a different example. Here we have Rachel, who has designed an experiment to test the effects of subliminal messages. While waiting for the experiment to begin, she measures the number of times participants yawn in a 10-minute period. Then she tells the participants that she'll be playing a recording that they should listen to while they're sitting in their chairs. During the next 10 minutes, music plays through speakers, but embedded in this music, someone's whispering, "Yawn, you feel like yawning," over and over. And she again measures the participants yawning. So what she wants to see is, like, while people are listening to this music and they're hearing that subliminal message, yawn, you feel like yawning, do they actually yawn more now than they did in the 10 minutes that occurred just before that? This kind of example is also going to use a t-test, but it's called a dependent t-test, and I'll show you why. It's not a single sample t-test, it's a dependent t-test or a dependent means t-test. Here's why. You'll notice that we're really getting from each participant two numbers. We'll get their yawn when the recording wasn't playing, and then we're going to get their yawns when the recording was playing. So like maybe the first person gave us a 2 when it wasn't playing, they were yawning twice, but when the recording was playing, they yawned 3 times. Maybe the second person only yawned once during those first 10 minutes, but the second 10 minutes they yawned twice. Maybe we got 2 more participants who never yawned at all. 0 the first time, 0 the second time, and so on. And so the question again is, does this recording, does it significantly affect the yawning? Now, what we're really doing is, our key to this kind of analysis is that we're going to be looking at difference scores. So we really want to test whether or not there's a difference from the first time to the second time. So we'll have that no record period, and then we have the recording period. And we want to go ahead and see if I say, for instance, participant number 1 has 2 during the no recording period and then 3 yawns during the recording period, the difference is 1. So if I take recording minus no recording, I get a 1. If I take the second person, take the recording number of yawns and subtract it from the number of yawns they had during the no recording, you can see it's also 1, and so on. So I have a bunch of different scores that I'm computing there, and these are what we're actually going to end up analyzing. So we're going to use these different scores just like we used scores on that geography test. They are what we're going to analyze to see if there's actually something significant going on here, whether or not that tape is actually increasing yawning. Here's our full data set for this particular problem. So again, I have 10 participants, and they're listed there, their participant numbers in the first column. And then you can see the number of yawns that happened when there was nothing playing, so while they were waiting for those first 10 minutes. And then we also have the 10-minute period when the recording was playing. And so you can see for each of the 10 people what happened the first time and what happened the second time. Now, you can figure out the means from those two, the number of yawns that they had for the no recording and the number of yawns they had for the recording. And you can see that they were 0.8 yawns on average when the first 10 minutes was going on. In the second 10 minutes, we're getting 1 yawn on average. So the difference really is we're getting 0.2 more yawns when the recording is playing. So that's really going to be our key, again, to analyzing, are we really getting something here? But we're going to analyze those differences. The column that I have there in red, that's where I took x2 and subtracted the x1. So I went ahead and took their recording again for x2, 3, and then the number of yawns they had for x1 and subtracted from it, and I got a 1, a 1, a 0, a 0, a 1, a minus 1, 1, 0, 0, and minus 1. All right, so those are all their differences. And if I look at the mean of all those differences, it turns out to be 0.2. So just like what we did before, if you treat those like those are the x's, and then there's the mean of the x's down at the bottom. So the differences are all the x's, and then the mean of those differences is what you see down at the bottom. That means that I can take each x or each difference and subtract the mean from it, and then square that, and I'll have square deviations. So you can see that in the next column over. I have what's called square deviations, where I take the difference, like the one that they had there for the first person was 1, subtract the mean from it, which is 0.2, square it, and I have now their square deviation for participant number 1. So for instance, it'd be like 1 minus 0.2, and I take that difference and I square it, and it ends up giving me 0.64 for their square deviation. And I do that for each person. The second one down gives me 0.64. The third person down gives me 0.04. Fourth person down gives me 0.04. I continue doing that all the way down. And then you can see I sum them all up and I get 5.60. So that's like my sum of squares. I'm getting my sum of all those square deviations that come from those different scores. Okay? So we've done a bunch of work here to kind of get us ready for the hypothesis test. And so again, you'll see that I'm just really focusing on those different scores and treating them like they're the original x's that we had on the previous example. So let's go through our 5 steps of hypothesis testing for this one. So step 1 is that we're going to restate the question as a research hypothesis and a null hypothesis about the populations. And here what we're going to do is we're going to say that the null hypothesis is that there's no difference. And so that would mean the mean of these differences was 0. So if the tape is really, this recording is really having no effect on the amount of yawning that's going on, then we wouldn't expect any difference from the last 10 minutes to the first 10 minutes. And so the mu is equal to 0 is the null hypothesis. If we end up rejecting the null hypothesis, we'll adopt this alternative, which is that the mu is not equal to 0, and we would have a significant effect. Now, step 2 is again determining the characteristics of the comparison distribution. So what I did is I just went ahead and used those numbers that I got from looking at my calculations. So the population mean here from the null hypothesis is mu is equal to 0. The population variance is an estimate from the sample. And this is again based on those deviation scores squared based on the differences. And so there you can see that my S squared is 5.6 over 9 or 0.62. So that's my variance. And remember we used n minus 1 here. And then if I take the square root of that, that's 0.79. So the standard deviation of those different scores is 0.79. The standard error then is I'm going to go ahead and compute one based on an estimate of the population standard deviation by plugging into the formula that you see there. So I want to go ahead and take 0.79 and divide it by the square root of n. And again, the square root of n here is the square root of 10, or 3.16. So if I take 0.79, the standard deviation of those different scores, and divide it by 3.16, I come out with an estimate of the standard error of 0.25. The shape of the distribution, again, is a t distribution with the degrees of freedom equal to n minus 1. And I'll end up having to look up that shape, that cutoff in table A2 for degrees of freedom of 9. Hypothesis testing for step 3 is similar to the previous example. We're going to determine the significance cutoff using the t-table. And again, we have degrees of freedom of 9. We're dealing with a two-tailed test. 2.262 is the alpha 0.05 for a two-tailed test where degrees of freedom is equal to 9. So if I go ahead and imagine my little curve here, a t-distribution where the degrees of freedom is equal to 9 again, I again have these boundaries of plus 2.262 and minus 2.262. Again, those will change depending on the degrees of freedom, but it just happens that these two examples both had degrees of freedom of 9. So my cutoff is plus or minus 2.262. Step 4 is that I need to now take my mean of these differences and figure out what the t is. So we're going to go ahead and figure this out. Our sample mean, or the mean of these differences scores, is 0.2. So I'm going to go ahead and plug in 0.2 for the m. Subtract the mu for the null hypothesis here is that there's no difference, so it's 0. So it's 0.2 minus 0. And then our estimate of the standard error for these different scores is 0.25. So that comes out to be 0.2 over 0.25, giving us a t of 0.8. So we have a t of 0.8. Now, we go ahead and compare this to our cutoff that was stated in step 3. That was plus or minus 2.262. Our obtained t was 0.80, so this doesn't exceed the cutoff, and therefore we do not reject the HO. So in a way, then, we've determined that the subliminal recording has no effect. It didn't actually increase yawning into any significant degree. That example, as I said, was called a t-test for dependent means, or a dependent t-test. The kind of design that we're actually using in that case was what's called a repeated measures design. So it's a design that we spoke about earlier in the semester. It's also called a within subjects design. So basically, a within subjects design is whenever the same people are tested twice, not game people, but the same people are tested twice. This could be before and after some procedure, like a pre-test, post-test design. It could be when there are two conditions in an experiment and the same people are tested under both conditions. Each of those cases are within subjects, okay? So it's either like before and after, like before the recording was playing versus after, or when there are just two conditions and the same people are tested under both conditions, like maybe you test them when it's hot outside and you test them when it's cold outside. This is also called repeated measures when you have different people matched in pairs. So you could have lots of identical twins and you have one twin do one thing and the other twin do another thing, and you compare the two twins on those different tasks. That would be also a repeated measures design. The key thing about any repeated measures design, though, as you can see, is that when we do this dependent t-test, or the t-test for dependent means, is that we're really always analyzing the difference or change scores. So in our example on subliminal advertising, we're just determining the differences for each person in the two conditions. And this could also be their post-score, pre-score, and so on. So anytime we've got two scores from a single person or from the same pair of identical twins, we're really analyzing the difference of those scores the way we did for a t-test for single sample means. Here's a nice table that's in your book, Table 7.7, that has the steps for a t-test for dependent means. It really has our 5 hypothesis tests. So step 1, again, is restate the questions, a research hypothesis and a null hypothesis about the populations. 2 is determine the characteristics of the comparison distribution. And that's when we made each person's 2 scores into a different score. We figured the mean of those different scores. We assumed a mean of the distribution of means of different scores where it was mu is equal to 0 because there was no effect. That's what the comparison distribution is like based on the null hypothesis. The standard deviation of the distribution of the means of different scores was as follows, and you can see how it summarizes those steps that we did. The shape of this t-distribution is degrees of freedom of n-1, so it changes based on how big the sample size is. 3 was to determine the cutoff sample, and we had to use table A2 to do that in the t-table. And in step 4 was determining our sample score on the comparison distribution by converting it to a t. And then 5, deciding whether to reject the null hypothesis by comparing the scores from steps 3 and 4. All right, so here's another example of a dependent means t-test. We have 109 students rate how close they are to their mother and to their father. So it's just a rating scale that tells us how close they feel emotionally to their mother and to their father. And the research question is, are these students equally closest to their mothers and fathers? For this example, we use an alpha 0.01 two-tailed. Note that this is a within subjects design because each person is providing us a score for one condition, their rating for their mother's closeness, and their score for their father. Okay, so let's go ahead and try to work this one out. For step 1, we're going to want to restate the question as a research hypothesis and a null hypothesis. So what we can say for the null hypothesis is that the difference between the father and the mother scores is equal to 0. So basically, we're saying that if I had the mean of all of the people's ratings for the father and all the ratings for the mother in the populations, I would look at the difference between the two and come out that it was 0. And if I reject that, then the alternative would be that no, they're not equal to 0. There's a difference in how close people feel to one parent over the other. Okay? Now, 109 people, that's a lot. So I'm going to go ahead and kind of speed up calculations a little bit here. So imagine here's what our data look like, that we have 109 students. And so for student 1, you can see the rating for closeness to their mother and the rating for closeness to their father. So they feel equally close to the two of them. Then what we want to do is take those 2 scores and come up with a different score, the difference between mother and father. So here you see it says 0. And then we would then go ahead and figure out the deviation, the difference of their different score from the mean of all the different scores. You can see down at the bottom of the differences that we have circled here, the mean of the different scores, which is 1.44. So you would take their different score, student 1's different score is 0, and subtract 1.44 from it and get minus 1.44. And then you would square that, and it comes out in the last column there, the square deviation of 2.07. And you would keep doing that for all 109 students. So there's a few more worked out here. There's student number 2's scores worked out, student 108, student 109. The key things that we need to know, though, are what's in circles. And so the circle here is that the mean difference between fathers and mothers is 1.44. So on average, people are rating mothers a little bit higher than they are their fathers in closeness. And that the sums of squares here, our square deviation sum, is 616.86. Okay? So we can take those numbers now and finish out step 2. Determine the characteristics of the comparison distribution. We want to know, for instance, the degrees of freedom. So degrees of freedom is n-1. So in this case, it's 109 minus 1, 108. So there's our degrees of freedom. The next thing I have listed here is we want to know the variance for this population that we're drawing the sample from. We're estimating it, so we're going to use the n-1 version of the formula. So you can see here is they have it as SS over DF, so the sums of squares, the square deviations total over the DF, or the n-1. So in this case, what we know is it's 616.86 over 108, and that gives us 5.71. So there's our estimate of the population variance, an unbiased estimate of the population variance. The mean of our comparison distribution was determined in step 1 because in our comparison distribution we say there's no differences between what people rate for their father and what they rate for their mother. So the population mean of this distribution of means is 0. Then what we want to do is figure out what the variance would be for the distribution of means, this comparison distribution. And so what we want to do then is take the variance estimate, which is s squared, and it turned out to be 5.71, divide it by the n, again, not the n minus 1 in this case, just the n, and that's 109, and that reduces to 0.0524. That's our variance of the distribution of means. The final step that we need in order to fully have all of our calculations done is we need to go ahead and figure out what the standard error is, or our estimate of the standard error. So in this case, we've already got the variance of the distribution of the means, so we can just take the square root of it, and it comes out to be 0.023. So that's our standard error estimate. And finally, the last thing you see there is the shape. The shape of the distribution, again, is a t-distribution where the degrees of freedom is equal to 108. So that's our shape of our comparison distribution. So those are all the things that we needed to do in step 2 about determining the characteristics of this comparison distribution, the thing that we want to see how our sample of different scores measures up to what would be defined by the null hypothesis. So in step 3, we're going to go ahead and determine the significance cutoff again using the t-table. We have to look at a different place on table A2 because we have a pretty high degrees of freedom here. Remember, it's 108. And if you actually look at the table, it stops really at 100, and then the next line is infinity. And you can see there's not much of a difference between 100 and infinity, but we'll go ahead and round closer to 100 and use 100 as our cutoff. So even though it's 108 is our degrees of freedom, we're really looking in the line that says degrees of freedom of 100. And remember, it's a two-tailed test, but the alpha, the problem said, is 0.01. So we're going to be a bit stricter here. And so for 0.01, that would mean then that our cutoff is 2.626. So we have now cutoffs of plus or minus 2.626. So again, here's our t-distribution where degrees of freedom is 108, and around plus 2.626 and minus 2.26 is where we can take the top 1%, or the 0.005 of each end of each corner here. Okay, we've done step 3. We're now ready for step 4. And in step 4, we want to go ahead and determine our sample score on that comparison distribution, right? So we want to convert our sample mean to a t. Now it says here our sample mean is 2.2, but that's actually a typo. It's really 1.44. So the sample mean here was 1.44. So the t is m minus mu over the sm, the same one that we used before. Our sample mean is, the mean of our differences is 1.44. We're going to subtract 0 from that because that's what the null hypothesis says, is there's no difference between mothers and fathers. And it's over an SM, or an estimate of the standard error, of 0.23 that we calculated there at step 2. So we get 1.44 over 0.23, and that gives us a pretty large t value of 6.26. So there's our t, 6.26. We want to go ahead and compare that then to our step 5 of our hypothesis testing, where we decide whether or not to reject the null hypothesis. The cutoff again for DF of 108, two-tailed, P is 0.01, was 2.626. Our obtained T was 6.26. So this does, it does exceed the cutoff. We want to reject the HO. So it does exceed the cutoff. The research hypothesis is supported. Students report having been closer to their mothers than to their fathers. So that is a significant difference there, is that people are saying that they feel closer to their mothers than they do to their fathers. So again, our obtained T was 6.26, so despite what I have typed on the slide, it does exceed the cutoff and we reject HO. The last topic that I want to bring up about t-tests at this point is some of the assumptions of these tests. And the first thing we want to do is just define, what does it mean to say that we have an assumption? Assumptions are circumstances that must be true for the logic and mathematics of a statistical procedure to work properly. So in the case of a t-test, there are assumptions that we have to make in order to be appropriately using the t-test for it to work appropriately. The major assumption for the t-test for dependent means is that the population distribution of these different scores is normal. So we're assuming that our samples were drawn from normal populations, and therefore their difference scores were normally distributed as well, because that's the major assumption for the t-test for dependent means. That assumption isn't usually a problem unless your original population is quite skewed. So for instance, if you're using reaction time scores, you'll have a very skewed distribution of values. And so there, it could be a problem for you to be using the t-test for dependent means. Or if you're using a really small sample size, that'd be another reason why the t-test for dependent means would not work very well, because you may not actually have a normal distribution, and by using a small sample size, you're not going to get a particularly good, you're not going to have a very robust test of the in the t-test here. The other final things to talk about are the effect size and power that we brought up with the z-test. Remember that the general formula for Cohen's d is it's the differences between the two population means over the standard deviation. In this case, what's in brackets is the mean of the differences on the two scores. So we were saying, whatever the differences between the ratings for moms and ratings are for dads, that's what's going to go in the brackets. And then the thing that's in the Greek letter symbol for sigma there is actually going to be replaced by S, the estimate of the population standard deviation. So that S that we calculated could go there. And so, for example, if the average difference is 6, that's the difference between the two population means, and S is 12, then the D would be 6 over 12, or 1/2, or 0.5. And we know from Cohen's conventions that 0.5 is a medium effect size. You can also figure out power, and you could figure out how much your power is based on your sample size and your effect size, and it would be determined from the tables like the ones in the book. I think perhaps the most important table is this one, table 712, that tells you how many research participants you're going to need when you're running a t-test for dependent means. So basically it's just telling us how many participants do we need in a repeated measures design. And you can see we can get by with fewer participants in a repeated measures design than we do when we were talking about having independent groups. So for a medium effect size, D is 0.5, and we're talking about a two-tailed test, we really just need 33 participants to go through the two conditions to have enough power, 0.8 power. If we have a larger effect size, we can get by with even fewer participants, like around 14. If we have a very small effect size, like 0.2, we're going to need 196 participants in our two-tailed test. So again, having a bigger effect size means I can get by with smaller participants. Okay, that's all I have to do right now in terms of introducing you to the t-test. Again, you want to go ahead and work through as many of these problems as you can at the end of this chapter. Look through those set 1 problems because they all have the solutions at the end of the chapter, at the end of the book, for you to see your answers. So if you work through some practice problems of t-tests in set 1, you can go ahead and get those answers and then go ahead and turn to the problem set A that's due for our next week. All right, that's it. That's all I have for now. Next time, we'll be talking about the independent t-test, the independent means t-test.